Hello, I'm Jonathan, and along with my partners here, Connor and Looning, we're going to talk a bit about a few interesting theorems in geometry, including the important Chavis theorem and the existence of something called the Nagel point. Now, first thing, we're going to have to go over some background info before we can get to these, so that's what I'm going to talk about right now. Quick reminder, we have a triangle ABC. Its area is determined by its heights and its base. So let's extend side BC and drop height H1 from vertex A, height H2 from vertex B to the opposite side AC. And we can extend side AB and get height H3 from vertex C. The area of the triangle, denoted K sub ABC, is equal to 1/2 times any of these heights times the length of the base that it falls to. Another thing we're going to have to define is a convenient thing called the semiperimeter. It's defined as follows. The semiperimeter is called S. We define it as 1/2 times A plus B plus C. What does that mean? Well, if we have a triangle, ABC, that's what we'll call it. Now, little a is the length of the side opposite vertex A. Little b is the length of the side opposite vertex B. And little c is the length of the side opposite vertex C. So the sum little a plus little b plus little c is just the perimeter of the triangle. We divide that by 2 and we get the semiperimeter, hence its name. The next thing we're going to talk about is a pretty cool object called an X-circle. They're kind of difficult to draw, but it's alright, we'll get through it just fine. The way we construct them is we'll start with our friend triangle ABC, and then we extend each of its sides. And we can extend them as far as we want. So there those are. The first circle we're going to draw is this, the X-circle opposite A, and then we'll have the X-circle opposite B, and finally the X-circle opposite C. Now if you'll notice, they're named as they are because, say, the X-circle opposite A is opposite vertex A. So they're named for the vertex that they're opposite. They are also tangent to the sides of the triangle. Now, for a curve to be tangent to a line, it has to just touch the line at one point without crossing. So the X-circle opposite A is tangent to side BC at point TA, the X-circle opposite B is tangent at point TB, and the X-circle opposite C is tangent at point TC. Now, the X-circles are also tangent to the extended sides at the points shown here. So each X-circle is tangent to 3 points. That's what makes the circle so special. Now what can we do with these? We can prove this theorem. The length of a tangent from a vertex of a triangle to the opposite X-circle is S, the semiperimeter. How can we prove this? Let's set up a triangle with a couple of extended sides. We'll call it X, Y, Z, just to change things up a bit. Here's the X-circle opposite X with its center O. It's tangent to the side ZY at point T sub X. It's also tangent to the extended sides at point P. There's the radius from O to P. And it's also tangent at point Q. There's its radius. We'll also include a line, XO. XO crosses the side ZY at a point we'll call R. Now, first let's notice that the length of PO is the same as the length of QO, since they're both the radius of the X-circle. Then we notice that the length XO is shared by two triangles, triangle XPO and triangle XQO. What can we do with that? Notice that XP is tangent, since it's tangent to the circle, is going to be perpendicular to the radius OP. We have the same thing with XQ and OQ. So angle XPO is equal to QO, which is equal to 90 degrees. Since we have a couple of right triangles here that have two equal sides, using the Pythagorean theorem, we can figure out what the third side of each triangle will be. Since the sides of these two triangles are the same, we find that they're congruent. And of course, we have that xp is equal to xq, two of the sides of those triangles. In the same way, we notice that zp is tangent to the x circle, and so is zt sub x. So we find that those are equal. Zp is equal to zt sub x. In the same way, yq is equal to yt sub x. Well, we know that xp is the sum of xz and zp, but xz plus zp, because of what we just showed a minute ago, that's equal to xz plus zt sub x. In the same way, we have that xq is equal to the sum of xy plus yq, which is equal to xy plus yt sub x. With a bit more algebra, we're going to add those two equations. So the sum of xp and xq is going to be xz plus xy plus zt sub x plus yt sub x. But we notice that zt sub x and yt sub x lie on the same line, so adding their lengths together gives us a length of side zy. So we have xz plus xy plus zy. But what's that? That's just the perimeter of the triangle, which is equal to twice the semi-perimeter of the triangle. And since we know that xp is equal to xq, we simply divide both sides by 2, and we get that both of them are equal to s. And it's proved. Now, we have some background out of the way, I'm going to pass it over to Looning, who's going to talk about Cheva's theorem. And then we'll use that theorem to, with Connor in a few minutes to prove the existence of the Nagel point.
Hi, my name is Looning. Today I'd like to talk about Cheva's theorem. In given triangle ABC, AD, CE, BF are the line connect their vertex to their opposite side of the triangle. They are concurrent in a common point O, then BD divided by DC times CF divided by AF times AE divided by BE equals 1. The first step to prove Cheva's theorem is to prove the area of two triangles with the same height are proportional with their base. What I mean by this is, in given triangle ABC, we connect the vertex A into their opposite BC with a line AD. Then we divide by the big triangle into two smaller triangles ABD and ACD. The area of ABD divided by area of ACD equals its base BD divided by CD. As we can see, the symbol K represents the area for the triangle. So the area of triangle ABD equals half the height times its base BD. Similarly, area of ACD also equals half the height times its base CD. So area of ABD divided by area of ACD equals half the height times BD divided by half the height times CD, which, since the height are the same, we can cross them out. You have BD divided by CD. Let's go back to original diagram here. As I proved in previous slide, BD divided by DC equals area of ABD divided by area of ACD. But they also equals area of OBD divided by area of OCD, because those two angles are proportional with the base with the same height. By using simple subtraction, area of ABD minus area of OBD equals area of AOB. Similarly, area of ACD minus area of OCD equals area of AOC. As we show on the diagram, BD divided by DC then becomes area of ABD minus area of OBD divided by area of ACD divided by area of OCD, which equals area of AOB divided by area of AOC. Let's apply this into another two-side triangle. Since I just proved BD divided by DC equals area of ABO divided by area of ACO. Similarly, in another two sides, ACF divided by AF equals area of BOC divided by area of ABO. And AE divided by BE equals area of ACO divided by area of BOC. So let's put these three sides into the same equation. BD divided by DC times CF divided by AF times AE divided by BE equals area of ABO divided by area of ACO times area of BOC divided by area of ABO times area of ACO divided by area of BOC, which we can cross the same triangle ABO, ACO, and the BOC, which we can get the answer of 1. So we just proved Travis theorem.
My name is Connor, and I'm going to talk about what the Nagel point is and how to prove its existence. We'll begin with triangle ABC denoted below. We'll next draw the 3 x circles of the triangle. Next, we're going to take each of the vertices and connect it to the point of tangency of the opposite x circle and the triangle. For example, starting with vertex A, we connect it to the point at which triangle ABC is tangent to the x circle opposite A. We're going to denote that point T sub A. We're going to do the same thing from vertex B to the point of tangency to the x circle opposite B, denoting that T sub B. Finally, we'll do the same thing with C, denoting that T sub C. The Nagel point is the point of intersection of all 3 of those line segments, as they are concurrent. Before we prove the existence of the Nagel point, we first need to discuss some of the lengths of a triangle related to the point of tangency to an x circle of that triangle. For example, here we have triangle ABC with the x circle opposite vertex A. We've denoted the point of tangency of that x circle with the line segment CB by T sub A. We've also denoted the points of tangency of the extended line segments of the sides of the triangle by P and Q respectively. Note that if the center of the x circle is point O, then the distances OP, OT sub A, and OQ are all the same, as they are all points on the circle. That distance is R, where R is the radius of that x circle. We showed earlier that AP is equal to AQ, and both are equal to the semi-perimeter of triangle ABC. We're going to denote the side lengths AC and AB by B and C respectively. Note that the length of line segment CP is equal to the length of AP minus AC. The length of AP, as we showed earlier, was just S, so the length of CP is just S minus B. Similarly, the length of CT sub A is also S minus B because both T sub A and P are points of tangency to a circle from point C. We know that the length of BQ is equal to the length of AQ minus the length of AB, and we know that the length of AQ is equal to S. So we get that the length of BQ is equal to S minus C. Similarly, we also know that the length of B to T sub A is also equal to S minus C because both of those are line segments to the points of tangency of the circle from the point B. Now we're ready to prove the existence of the Nagel point. We begin with triangle ABC, and we connect each vertex to the point of tangency to the x circle opposite that vertex, as we did before. We denote those points T sub A, T sub B, and T sub C as shown in our diagram. We know that by Cheva's theorem, which we talked about earlier, these three line segments are going to be concurrent. That means they all intersect in the same spot if the product A T sub C over B T sub C times B T sub A over C T sub A times C T sub B over A T sub B is equal to 1. While going through some of those lengths, we know from our last slide what they're equal to. For example, the line segment A T sub C, as we showed earlier, is equal to the value S minus A. So we drop that down over to the right and make note of it. Similarly, the line segment B T sub C is going to have a length of S minus B. So we jot that down. In the same vein, the line segment B T sub A is going to have a length of S minus B, and we jot that down. Again, the length of line segment T C sub A is going to be S minus C, and we write that down. Also the same way, the line segment C T sub B is going to have a length of S minus C, and we jot that down. To finish off, the line segment A T sub B is going to have a length of S minus A, and we finish off our chart with that. Using our chart to the right, we're now going to replace the values of the line segments with the lengths we found. That's going to yield us an identical equation that will be S minus A over S minus B times S minus B over S minus C times S minus C over S minus A. As you may have noticed, these values can cancel out. For example, S minus B cancels out with each other, S minus C cancels out with each other, and finally S minus A cancels out with each other. This means that we're left with an overall value of the equation of 1, which by Cheva's theorem means that those three line segments are all concurrent and all meet at one point. And we're going to call that point the Nagel point and denote it N. Thank you very much.